Imagine standing beneath a sky where rain doesn't cool the air, it burns through it. Not because of lava, not because of fire, but because every single raindrop is made of molten iron. It sounds like something invented for science fiction, yet astronomers have confirmed that such a world actually exists. Hundreds of light years away, a giant planet is locked in a cosmic struggle so violent that iron itself evaporates into the atmosphere, rides powerful winds across the planet, and falls back to the surface as liquid metal. The planet is called WASP S76b, and the deeper scientists looked, the stranger it became. Because this isn't just a planet with unusual weather, it's a place where the laws of weather, chemistry, and even day and night behave in ways that challenge everything we thought we knew about worlds beyond our solar system. The discovery began with a simple question: could distant planets have weather? For years, astronomers could detect planets orbiting distant stars, but they knew almost nothing about what those alien skies looked like. Most exoplanets appeared only as tiny dips in starlight, small shadows crossing enormous stars. The planets themselves remained invisible. Then technology changed everything. Powerful observatories began analyzing the tiny fingerprints left in starlight as planets passed in front of their stars. Every gas absorbs light differently. By studying those missing colors, scientists could identify the chemicals floating in alien atmospheres. Suddenly, distant worlds weren't just dots on a chart anymore. They had clouds, they had winds, they had temperatures. Some even had storms. Then astronomers pointed their instruments toward one particular star nearly 640 light-years from birth. Orbiting it was a massive gas giant, unlike anything in our own solar system. Its name was WASP S76b. At first glance, it seemed similar to Jupiter, but that comparison quickly fell apart. Jupiter takes nearly 12 Earth years to orbit the Sun. WASP S76b completes an entire orbit around its star in less than 2 Earth days. Think about that for a moment. A full year lasts under 48 hours. That means the planet is unimaginably close to its star. Closer than Mercury is to our Sun. So close that gravity has completely transformed it. One side of the planet always faces the star, the other never sees daylight. Just like the Moon always shows the same face to Earth, WASP S76b has become tidally locked. Its day side never experiences sunset. Its night side has never witnessed sunrise. One hemisphere exists in endless daylight. The other remains trapped in eternal darkness. That alone would create an extraordinary world, but scientists soon realized something even more extreme was happening. The star-facing side reaches temperatures above 2,400 degrees Celsius, hot enough to melt many metals. Even iron cannot remain solid there. Instead, rocks begin to vaporize, metals evaporate into the atmosphere. Iron becomes gas. Picture mountains on Earth slowly turning into vapor beneath a relentless white-hot sun. That's everyday reality on WASP S76b. The atmosphere itself becomes loaded with vaporized metals, iron, magnesium, calcium, perhaps even traces of titanium. Everything begins behaving differently under such unimaginable heat. But heat wasn't the greatest surprise. Movement was. Because this planet doesn't simply bake beneath its star, its atmosphere is constantly in motion. Extreme temperature differences between the blazing day side and the cooler night side generate unbelievably powerful winds. These aren't hurricanes, they're atmospheric rivers traveling at thousands of kilometers per hour, faster than the speed of sound on Earth. Imagine jet streams carrying entire oceans across the sky.
That's essentially what's happening. The scorching day side continuously produces vaporized iron. Powerful winds grab that metallic vapor and transport it across the planet towards the dark hemisphere. There, something remarkable occurs. Temperatures drop, not enough to become comfortable, not even remotely close. The night side still reaches well over 1,000 degrees Celsius, but compared with the inferno on the day side, it's cold enough for iron vapor to condense, exactly as water vapor forms clouds on Earth. Except these clouds aren't made of water, they're made of iron, molten iron. Eventually, those clouds become heavy. Gravity does the rest. Liquid iron falls through the atmosphere. Iron rain. Real, measured, scientifically supported. When this idea was first proposed, it sounded almost unbelievable. Even many astronomers approached it cautiously. Extraordinary claims require extraordinary evidence. Fortunately, evidence was exactly what scientists began collecting. Using one of the world's most advanced observatories, researchers examined subtle changes in light passing through the atmosphere of WASP S76b. They weren't searching for rain directly. That would have been impossible. Instead, they searched for iron itself. Specifically, they looked for where iron appeared and where it mysteriously disappeared. The results were astonishing. On the evening edge of the planet, where scorching daylight transitions into darkness, iron signatures weakened dramatically. Meanwhile, stronger signals appeared on the intensely hot side. The simplest explanation fit perfectly with theoretical predictions. Iron gas formed on the day side, atmospheric winds carried it across the planet, cooling caused condensation, the iron fell from the sky before returning to hotter regions where it evaporated once again, an endless planetary cycle. Earth has the water cycle, WASP S76b has the iron cycle, and suddenly weather became far more strange than anyone imagined possible. Yet that wasn't the only mystery. Scientists noticed that the atmosphere wasn't behaving symmetrically. The hottest point on the planet wasn't located directly beneath the star. Instead, it appeared shifted. Something enormous was redistributing heat around the globe. That meant the atmospheric circulation wasn't random. It was organized, stable, persistent, powerful enough to move staggering amounts of energy from one hemisphere to another. Models suggested continuous superheated winds racing around the planet at incredible speeds. Entire weather systems larger than Jupiter itself. No human experience offers a true comparison. On Earth, weather changes daily. On WASP S76b, weather may rage almost continuously. The atmosphere never rests. The star never sets. The furnace never cools. Then astronomers discovered another strange detail. The planet itself isn't perfectly round. The intense tidal forces generated by its nearby star stretch the planet into a slightly distorted shape. Gravity is literally pulling the world apart, not enough to destroy it immediately, but enough to reshape it. Imagine a planet constantly squeezed and stretched by the gravity of a neighboring star. Every orbit, every day, every year lasting less than 48 hours. The closer scientists looked, the impossible this place seemed. Yet every new observation confirmed it was real. And then another question emerged. If iron can rain on one planet, what other impossible weather might exist across the galaxy? Clouds of gemstones, glass storms, oceans of lava. Suddenly, the universe seemed far less familiar. WASP S76b wasn't simply an oddity. It was proof that planets could evolve into environments no human imagination had ever predicted. But one observation still refused to fit neatly into the story. Scientists expected iron rain to occur only under certain atmospheric conditions. Instead, the data hinted that something else, something even more powerful might be influencing the planet's atmosphere, a hidden force, one capable of reshaping winds, temperatures, and even the chemistry of the sky itself. If confirmed, it would mean molten iron rain isn't the most extraordinary thing happening on WASP S76b. It would only be the beginning.
If molten iron rain wasn't the biggest surprise on WASP WS76b, then what was? To answer that question, scientists had to look beyond the rain itself and study something far more difficult to observe: the invisible forces controlling the entire atmosphere. On Earth, weather is driven by sunlight, oceans, mountains, and the planet's rotation. On WASP WS76b, almost none of those familiar systems exist. There are no oceans of water, no continents, no forests, no seasons. Instead, the entire atmosphere is trapped between two permanent extremes: endless daylight and endless night. That creates one of the strongest temperature contrasts ever measured on a planet. Nature always tries to balance extremes. Hot gas expands, cooler gas contracts. The result is constant motion. On WASP WS76b, that motion becomes global. Scientists estimate that winds race around the planet at several kilometers per second, many times faster than the most powerful hurricanes ever recorded on Earth. These winds don't simply move clouds, they transport heat, metals, and enormous amounts of energy from one side of the planet to the other. Without them, the day side likely would become even hotter, while the night side would cool dramatically. Instead, the atmosphere behaves like a giant conveyor belt. It never stops moving. But observations revealed something unexpected. The atmosphere wasn't perfectly following the predictions made by early computer models. Certain chemical signatures appeared where they shouldn't. Other signals were weaker than expected. Some regions seemed hotter than calculations suggested. Others looked cooler. That meant scientists were missing an important piece of the puzzle. One possibility involved chemistry. At temperatures above 2,000 degrees Celsius, molecules begin breaking apart. Atoms that normally stay bonded become separated. New compounds form. Old ones disappear. The atmosphere becomes an active chemical laboratory, unlike anything naturally found on Earth. Iron isn't the only material affected. Astronomers have also detected evidence of sodium, calcium, magnesium, and other elements in similar ultra-hot giant planets. Each one responds differently to temperature and pressure. Together, they create an atmosphere that changes from one hemisphere to the other in ways scientists are still trying to understand. Then came another fascinating idea. What if the iron isn't falling everywhere? On Earth, rain isn't evenly distributed. Some places are deserts, others receive constant storms. The same could be true on WASP WS76b. The iron rain may be concentrated in enormous storm systems that circle the planet continuously. Instead of scattered thunderstorms, imagine vast rivers of metallic clouds stretching thousands of kilometers across the sky. Beneath them, glowing droplets of molten iron would fall into an atmosphere hotter than a blast furnace. No human technology could survive there. Even spacecraft built from advanced alloys would face incredible challenges. The temperatures alone would destroy most familiar materials. And yet, despite its hostile environment, WASP WS76b has become one of the most valuable laboratories in modern astronomy. Why? Because planets like this help answer questions about planets everywhere. When astronomers first began discovering exoplanets in the 1990s, many expected to find systems similar to our own.
Instead, they found hot Jupiters, giant planets orbiting astonishingly close to their stars. At first, scientists thought these worlds might be rare. Now we know they're surprisingly common. That forced researchers to rethink how planetary systems form and evolve. Many of these giant planets probably didn't form close to their stars. Instead, they likely formed much farther away, where temperatures were low enough for massive planets to grow. Over millions of years, gravitational interactions gradually pulled them inward until they reached incredibly tight orbits. WASP WS-76b may be one of those migrants. Its present location is probably not where it was born. That journey transformed it into the world we observe today. The closer it moved towards its star, the more intense the radiation became. Its atmosphere expanded, its chemistry changed, its weather grew increasingly violent. Eventually, it reached a point where iron itself could no longer remain solid. In a sense, the planet became a natural experiment in extreme physics. Every observation teaches scientists something new about matter under extraordinary conditions. Then came another mystery appeared. Some astronomers believe planets this close to their stars slowly lose parts of their atmospheres. Powerful ultraviolet radiation can heat the outer layers until gas begins escaping into space. If that process continues for millions or billions of years, an entire planet can gradually shrink. Scientists are still investigating whether WASP WS-76b is experiencing significant atmospheric loss, but many ultra-hot giant planets show evidence that their stars are slowly stripping material away. If true, the world we see today is only a temporary stage in a much longer cosmic story. Nothing lasts forever, not even planets. As technology improved, new telescopes began revealing even more detail. The arrival of next-generation observatories, including the James Webb Space Telescope, has opened a new era in exoplanet science. Instead of merely detecting planets, astronomers can now analyze their atmospheres with unprecedented precision. Every observation adds another piece to the puzzle. Scientists can estimate temperatures, identify molecules, measure atmospheric circulation, study cloud formation, search for unexpected chemistry. The dream that once seemed impossible, studying weather on worlds hundreds of light years away, is rapidly becoming reality. And the surprises keep coming. Researchers have found planets where clouds may contain silicate minerals, the very basic ingredients found in rocks on Earth. Others appear hot enough for vaporized metals beyond iron. Some worlds may experience fierce winds carrying mineral particles through the atmosphere like endless sandstorms. Each discovery expands our understanding of what a planet can be.